let's talk about vector functions, which has a new name, but it's not a new idea for you. Here we have three parametric equations, one for x, one for y, one for z. You've done these, all right? You know what's up with parametric equations. You know that, say, when t is 0, we get the point e to the 0, which is 1, sine of 0, 0, 1 over 0 plus 1. So we get the point 1, 0, 1, right? And then as t starts changing, we start generating different points. We play connect the dots, boom, there's a curve. It can be inconvenient to have these equations just kind of sprawling out all by themselves. And so what we do to make things a little bit more efficient is bundle them together into a vector. And then this is what's called a vector function. This vector has components that are now changing as t changes. That's a function. It's a function of t. In this case, the x component is the function e to the t, the y component is sine of t, and z is 1 over t plus 1. The way we visualize this curve in this vector setting is we imagine a paintbrush anchored at the origin, and then we have a vector, which is the paintbrush, and as t changes, this vector, which is pinned to the origin, will sweep around in space and be drawing a curve based on these components. So when t starts at 0, we already mentioned we start at 1, 0, 1 for this particular vector field. So that is x is 1, y is 0, z is 1. So that starts kind of straight up in space like that. And then by the time we get to t equals pi, we are going to be at e to the pi, which is a very large number, sine of pi, which is 0, and 1 over pi plus 1, which is a small number. So as t evolves from 0 to pi, you can imagine this curve starts to behave such that its x-coordinate is getting bigger and bigger from 1 to e to the pi. The y component gets a little bigger and then a little smaller. So the y component is actually going to sweep out into the plane, but into the octant, but then come back to 0. And then the z component is just going to get smaller and smaller. And so this curve might do something like this, which is hard to kind of sweeps in, sweeps back out, but it's coming down towards the xy plane. It's hard to visualize the details of the curve, but the idea is that as t changes, these functions are changing, so the components of the vector are changing, and so this vector draws out a curve in space. If we had x equals cosine t, y equals sine t, z equals t, we would have a helix. You've already seen that from parametric equations. So this is what a vector function is. And having a vector function, just like all sorts of other functions, there are limits to be found. There are derivatives. There are integrals. So this is one of those cases where Calc 3 is much more a continuation of Calc 1 than Calc 2, because all of these problems that you're going to see with vector functions are exactly like Calc 1 problems. It's just that in this case, for example, there would be 3 little mini problems involved in one large problem. So for example, let's say I gave this a name, right, because we like to name our functions. So we'll call it R. Let's save F for scalar functions. So R tends to be a typical word, a typical letter to use for vector functions. E to the t sine t 1 over t plus 1. So now it has a name, which means now we can do things like ask for the limit as t approaches pi over 2 of r of t. Well, you might imagine, or you at least might hope, that to do the limit of this whole function, you just have to do the limit of the individual components. And that's what happens. So as t approaches pi over 2, e to the t approaches e to the pi over 2. As t approaches pi over 2, sine of t approaches 1. And as t approaches pi over 2, z approaches 1 over pi over 2 plus 1, which is going to be 2 over pi plus 2. I hope. Right? So limits behave just like that. We could find r prime. Well, you might hope that the derivative of the whole function would just be the derivatives of the individual component functions, and that's true. So there's r prime. You might imagine that we can do an integral of r. Whoops, sorry, it's not supposed to be r prime. I'm going back to the original r. It would be with respect to t, because this function is a function of t. This is a little bit trickier, but only because of the arbitrary constant business. Because the antiderivative of r is going to be the collection of the antiderivatives of the individual functions. So that means, e to the t plus an arbitrary constant. Integral of antiderivative sine t is negative cosine t plus an arbitrary constant. Antiderivative of 1 over t plus 1 is natural log of t plus 1 plus an arbitrary constant. And now here's the thing. Those can't be the same constants because each of them has to be arbitrary. So let's say we numbered them 1, 2, and 3 like that. We could actually separate the constants out and we would have a whoops, I'm off the screen. Pardon me a sec, I'll lift it up. I'm at the very end here, so I don't want to change paper. If I take e negative cosine natural log as one vector, I could add on a vector of c1, c2, c3, which is just a vector with 3 arbitrary components. So let's call it an arbitrary vector. And so this is really the subtle difference in antiderivatives of vector functions is you don't just generate one arbitrary constant, you actually generate an arbitrary vector. So when you get into the notes and the examples, you're going to be handed vector functions, you're going to be asked for evaluations, limits, derivatives, antiderivatives. Hey, here's an antiderivative where we have a data point we need to go through. That means you're going to be able to find your arbitrary constant. You'll see problems where this happens to be a position function, which means the derivative is a velocity function, and the second derivative is an acceleration function. And since you can do all of these things, you could be given a velocity function and recover the position function through all these operations that you're used to. So that's just an opening glimpse into vector functions. Go have a look at the notes and try some problems. Let me know when you have questions.